Okay, so welcome everyone to the seminar at LIP. Today we are pleased to have Meytal Duer as the speaker. So Meytal graduated in 2019 from Tel Aviv University in Israel in experimental nuclear physics. And this work was actually recognized with the Eisenberg Award for Academic Research Excellence. So since then, she's a postdoc in the Technical University of Darmstadt, where she leads the cluster project Elements, aiming at exploring the universe from microscopic to macroscopic scales. And Meytal is also part of the R3D collaboration in the International Accelerator Facility Fair in Germany for studies of reactions with relativistic radioactive beams. And within this scope, she works closely with our LIP colleagues of the nuclear group at LIP. So today she will speak about short-range correlated nucleon pairs in nuclei. So Meytal, you can start when you want.
Okay. You can see my screen, right? And hear me okay?
Yes, yeah, we can.
Perfect. Okay, so thank you for the introduction and good morning, everyone. As already presented, my name is Meytal Duer from TU Darmstadt. And first, I would like to thank Daniel for inviting me to give this seminar, where indeed today I will talk about the experimental study of short-range correlated nucleon pairs in nuclei, and in particular in neutron-rich nuclei. So let me start from some basics nuclear physics. Now, a fundamental aspect in nuclear physics is to understand the nature of the strong interaction which makes up the atomic nuclei and determines their properties. So if we have a nucleus with A nucleons, in order to get a full description of it, one has to go and solve the many-body Schrödinger equation, which is defined by the many-body Hamiltonian. We have the kinetic energy term and then a contribution from two-body nucleon-nucleon interactions, and possibly even higher order terms. Now, this is, of course, a very complicated problem to solve, and it becomes extremely challenging for a nucleus which has more than just a few nucleons. So the first successful description of the atomic nuclei was the nuclear shell model. And in this picture, we consider the nucleus as a collection of individual nucleons that move under the influence of a mean field potential that is created by all other A-1 nucleons. Looking at the protons and neutrons, they would populate independently of each other. And of course, according to the Pauli exclusion principle, the different energy states up to the Fermi energy level. So we have the single particle shell model based on the mean field approximation. And in order to test the model, different experimental techniques can be used, such as electron scattering. And since the electromagnetic interaction is well understood, electron scattering has long been used as a probe in order to investigate the nuclear structure. So in this case, we have the incident electron that knocks out a single nucleon from the nucleus, usually a proton. Then after the reaction, both the electron and the knocked out proton are scattered and detected in a coincidence. And this is what we refer to as an AEE'P measurement. Now, in the plane wave approximation, we describe the reaction in terms of a single photon exchange. The electron transfers a virtual photon with momentum q and energy omega to a single proton in the nucleus, and then leaves the nucleus without reinteracting. The proton, which had the initial state momentum pi, gets an additional momentum in the reaction. Now, depending on the energy that is transferred in the reaction, we can then probe different parts of the nucleus. Here we can see the electron-nucleus spectrum as a function of the energy transfer. The lowest energy peak corresponds to elastic scattering of the nucleus as a whole. On the other hand, at large energy transfer, the reaction is dominated by deep inelastic scattering, which is sensitive to the internal structure of a nucleon. Then we have the region of interest, the quasi-elastic peak, which is identified as scattering of a single nucleon within the nucleus. And basically, we are using the term quasi since this is the equivalent to elastic electron scattering of a free nucleon, just that now the nucleon is bound inside a nucleus. And in an experiment, by measuring the momentum of the outgoing electron and the knocked out proton, we can define what we call the missing momentum and missing energy of the reaction, which, assuming no final state interactions occurred after the reaction, represent the initial momentum of the knockout proton within the nucleus and its separation energy. Now, the success of the shell model came from its ability to describe correctly many properties of the nuclei. Here we see a typical example for an E'(P) measurement from a p-shell nucleus, oxygen-16. In oxygen, we have 8 protons, and the observed peaks that we can see here in the missing energy distribution match the separation energy values which are predicted for outer p-shell protons. Then if we look at the momentum distributions of these protons from the p1/2 and p3/2 states, they are consistent with the calculations performed within the mean field approximation. So the mean field calculations describe the data well, but except for the fact that the measured strengths in the data compared to that expected from the calculation does not equal to 1 and is about 0.7. So this means that the experiment only measured about 70% of the expected strengths of p-shell protons. And this reduction in the strengths between measurements and calculations was observed for a wide range of nuclei, from light ones to heavy nuclei. In all measured cases, the ratio between the measured cross-section for a single proton knockout compared to that expected from calculations is between 60 to 70%. So basically, the shell model does not provide a consistent picture of the occupancy of the nuclear orbitals, such that only about 60 to 70% of the nucleons can actually be described as independent nucleons, meaning that the remaining 30 to 40% must be part of higher order configurations. Now, since the mean field approximation is a one-body approximation, the natural step going beyond it is to include correlations between nucleons, nucleon-nucleon interactions. And in general, the correlations can be classified in terms of the relevant distances they are sensitive to in the nucleon-nucleon potential. So in principle, we have two kinds of correlations: long-ranged, which go like the nucleus radius, and short-range correlations, which go like the nucleon radius. Now, even when considering long-range correlations like pairing, this reduction in the strength still remains between 25 to 30%. So the wave function of a nucleus can be decomposed into components at different momentum regions. The first part, that is the valence space, the single particle and pairing correlations. Then we have a contribution from coupling to high energy excitations, which are not included in the valence space. And the last term represents the contribution from short-range correlations, which I will focus on here today, where its strength was estimated to be between 15 to 20% of the wave function. Now, in terms of the nucleon-nucleon interaction, overall it is dominated by the scalar part of the interaction, which goes from attraction at typical nucleon separation to the strong repulsive core at very short distances. But in between, at the region of short distances I refer to, where it approaches zero, it is now the tensor part, which is spin isospin dependent, that becomes important. And in particular, this region is of interest when we consider different nucleon-nucleon models that describe the interaction. They all contain parameters which are determined experimentally and are not well constrained at short distances or equivalently at high momentum. And this leads to a large model dependence at high momenta, so very different predictions depending on the model which is used. Now, this short tensor attraction induces short-range correlated nucleons. In the nucleus, the average distance between nucleons is about 1.8 Fermi, and the nucleus behave approximately as independent particles in a mean field potential. But as the nucleons are moving in the nucleus, two nucleons can get close enough together such that temporarily they experience the short-range part of the interaction and cannot be described as mean field nucleons. And these are two nucleon short-range correlations, SRC. A pair of nucleons that are close together within the nucleus at a typical distance of about 1 Fermi. Now, due to their close proximity, the local density is several times larger compared to the normal nuclear saturation density. And these are densities that exist, for example, in the core of neutron stars, but are difficult to measure in the lab. And therefore, the study of short-range correlations can actually teach us not only about the fundamental nucleon-nucleon interaction, but might also be used as a probe to high densities. Now, in the momentum space, we define them as a pair of nucleons that each has large momentum and their two momenta balance each other. Or is that, in other words, a pair with large relative momentum and small center of mass motion. Now, always large and smaller relative to the Fermi momentum of the nucleus, which has a typical value of about 250 MeV/s. Now, the existence of short-range correlations is evidenced from the momentum distributions of the nucleons in the nucleus. For simplicity, if we consider the nucleus as a free Fermi gas, then the nucleons will simply fill up the different momentum states according to the Pauli exclusion principle up to the Fermi momentum, leading to a step function in the momentum distribution. Then if one takes a more sophisticated one-body potential, we expect a certain distribution at the region of low momentum below the Fermi momentum, and only a small fraction above it. But calculations which use realistic nucleon-nucleon interaction clearly show a high momentum component, what we call the high momentum tail, which cannot be reproduced without taking into account correlations and assuming only the single particle picture. And in addition, this behavior at high momentum was found to be universal. So same for all nuclei, whether we consider light, medium mass nuclei, or even heavy nuclei. In all cases, we expect this high momentum tail. So in principle, whenever we talk about high momenta, we talk about SRC pairs. So now let us see how do we probe these pairs experimentally. The experimental study of short-range correlations has in fact a long history, but here I will focus only on what we call hard knockout reactions. So this means that we have a high energy probe, again, usually an electron, and we consider reactions with large momentum transfer. And this to ensure us that the scattering is done of a single nucleon. So we have the incident electron that knocks out one of the nucleons of the SRC pair. So basically it breaks up the pair. Then the electron and the knocked out nucleon are both scattered and detected. Finally, after the breakup of the SRC pair, the correlated partner will recoil according to its high momentum and will be detected in a coincidence. So in principle, we are talking here about a triple coincidence measurement, which then allows us to go and reconstruct the initial state of the two nucleons in the nucleus. So how do we actually reconstruct this initial state in terms of measured quantities? First, similar to what we saw before, from the momenta of the incoming and outgoing electron, we define the momentum transfer of the reaction, so the momentum of the virtual photon. And then by measuring the momentum of the knocked out nucleon after the reaction in the final state, we can reconstruct its initial momentum. For the high momentum correlated partner, it should simply recoil with momentum that is equal to its initial momentum. Now, this is of course only true in case where we don't have contributions from other competing processes or final state interactions that could lead to the same measured final state. So the idea is basically to select a specific kinematics that will minimize the contribution from competing processes and suppress the final state interactions. After that, the remaining final state interactions might be treated using the Glauber approximation, which shows good agreement with data, as in the example that we can see here for the nuclear transparency, which is basically the attenuation of the outgoing nucleons as they go through the nucleus. And in addition, calculations show that the final state interactions are mainly confined within the SRC pair and not with the residual A-2 system. And this implies that certain quantities are not sensitive to the final state interactions, such as the center of mass motion of the SRC pair, as well as its isospin structure. So up to now, most of the knowledge that we have about SRC comes from electron scattering experiments, performed at Jefferson Lab in the US. And it operates a continuous electron accelerator where the electrons can be accelerated up to maximal energy of about 12 GeVs. And this was about 6 GeVs at the time the measurements I will present here were performed. After that, the electron beam can be delivered into 1 out of 4 different experimental halls where each hall is equipped with a different setup of detectors. And in fact, SRC measurements were performed in each of the experimental halls, where the results that I will show in the next slides are from measurements performed at Hall B. So Hall B has a large acceptance spectrometer class, where the detector has kind of like an onion shape with different shells of sub-detectors that are used to identify and measure the momenta of the different particles. Now, the great advantage of class is, of course, its large acceptance of almost about 4 pi, which allows us to detect several particles in the final stage. So first, it was confirmed that the high momentum tail that we saw in the momentum distribution is indeed populated almost exclusively by SRC pairs. By looking at the ratio between the number of high momentum knocked out protons, which are accompanied by a correlated partner, either a proton or a neutron, to the total number of high momentum protons, we can practically see that all high momentum protons come in pairs. And this was shown to be a universal feature also for heavier nuclei. In all measured cases, about 20% of the nucleons come from SRC pairs. Then some characteristics of SRC pairs were observed. For example, the opening angle between the 2 nucleons of the pair, where here we can see clearly the SRC signature, back-to-back correlation around 180 degrees. Another fundamental characteristic is the center of mass motion. And by measuring the momenta of the 2 nucleons, we can reconstruct their center of mass momentum distribution, which is normally distributed around 0 and has a corresponding width of about 140 MeV per C for the case of carbon-12. Now, if we consider the center of mass width for different measured nuclei, the width increases only little from carbon-12 to heavier nuclei, and it's consistent within the uncertainties with a constant value, as well as with the sum of 2 mean-field nucleon momenta, which are presented here by the different black lines. And this supports the picture that SRC are formed as temporal fluctuations of mean-field nucleon pairs. Now, an important characteristic of the short-range interaction is the predominance of neutron-proton pairs, what we call NP dominance. If we look at the ratio between the measured number of proton-proton pairs to neutron-proton pairs, we see that we have many more NP pairs, about 20 times more, and this is seen for all measured nuclei, whether we consider the light symmetric carbon-12 or the heavy asymmetric lead-208. And this therefore shows the universality of the short-range interaction, which even in lead, although we have about 50% more neutrons than protons, it is still dominated by NP pairs. Now, this NP dominance basically originates from the dominance of the tensor interaction at short distances or high momenta that we saw before, where the scalar part approaches zero. So the tensor interaction, which is again spin isospin dependent, has a very strong preference to neutron-like NP pairs with spin 1 and isospin 0 compared to spin 0 PP pairs. And this is also seen in ab initio calculations. In the example that we see here, the two-body momentum distributions were calculated using realistic 2- and 3-body interactions. So the NP and PP distributions are shown here as a function of the relative momentum between the two nucleons of the pair for zero center of mass momentum, so back-to-back nucleons. And what we see here is that at short distances, that corresponds to momenta in the range between 300 to 600 MeV per C, there is clearly an excess strength for NP pairs compared to PP pairs which have a node. Now, in the last few years, an effective theory which has been used in order to describe SRC nuclei is the generalized contact formalism, or the GCF. And the basic assumption of this formalism is that at high momenta, the many-body wave function can be factorized into two parts. So first, a universal function, which is nucleus independent, that describes the SRC pair, and it depends only on the nucleon-nucleon potential, which is used as an input. And secondly, a function which is nucleus dependent, that describes the residual A-2 system. Now, the sum that we see here goes over the different SRC channels. So under this assumption, we can go and write the single proton momentum distribution as a sum of the different contributions from SRC pairs. The main contribution comes from neutron-like NP pairs with spin 1. And for spin 0, we have two contributions, either NP pairs or PP pairs. And of course, similarly, we can write the single neutron momentum distribution. Then this formalism was tested by comparing it to ab initio calculations, where overall it shows a good consistency. In a similar manner, we can also then write the two-body momentum distribution, which allows a comparison to data from the knockout measurements that also shows a good agreement. So now we can actually go one step further and to look at the transition between the region that is dominated by the tensor part back to the scalar part of the interaction and the repulsive core. And we can do that by looking at higher momenta. So of course, as the relative momenta between the two nucleons of the pair increases, their spatial separation decreases, and therefore we expect a transition between the spin-dependent tensor force to the spin-independent scalar interaction. So here we consider the fraction of PP pairs as a function of the missing momentum, which is again equivalent to the initial momentum of the knocked out proton in the nucleus. So larger missing momentum corresponds to shorter distances. And what we see here is that for momenta in the range between 400 to 650 MeV per C, the fraction of PP pairs increases, which is consistent with a transition from the tensor to predominantly scalar part of the interaction. Above 700 MeV per C, it seems to flatten out. And this is also consistent with the scalar limit, where contribution from all pairs should be equal. Then the measured rushes were compared to calculations which were performed within the generalized contact formalism, using the commonly used AV18 interaction as an input, which shows a good agreement, as well as chiral EFT interactions with different momentum cutoffs, which are therefore not expected to show good consistency at very high momentum. Now in blue, we see another calculation, but based on a simplified interaction, which does not include the tensor force. So in contrary to the other interactions, the NP momentum distribution has a node at this momentum region, leading to an increased fraction of PP pairs, which is clearly in disagreement with the data, demonstrating again the dominance of the tensor force. So now I want to focus on neutron-rich nuclei and to look separately at the protons and the neutrons. Now, without the short-range interaction, since we have more neutrons in the nucleus, they occupy higher momentum states and therefore have, on average, higher momentum. But with the short-range interaction, due to the NP dominance, we have the same number of high momentum protons and neutrons in this high momentum tail. And in general, this increases now the average momentum of the protons. But still, since we are talking about neutron-rich nuclei, we have more neutrons in the nucleus. So the question is basically, what do these excess neutrons do in terms of correlations? The first possibility is that they simply do not correlate. Then a different possibility is that they do correlate with core protons or maybe even with each other. In order to answer this question, we consider the dynamics of the protons and neutrons with the neutron excess by looking at what we call the correlation probability. So that is the fraction of high momentum nucleons in a nucleus A relative to carbon-12, which basically serves as a reference. And we consider it separately for protons and neutrons. Now, for the protons, we can clearly see that their high momentum fraction increases with the neutron excess, while for the neutrons, it stays more or less constant, so saturates. And this means that indeed, although we have more neutrons in the nucleus, they do correlate with core protons, such that when we move from symmetric to neutron-rich nuclei, the protons basically speed up in this kind of neutron-rich nuclei. And this finding can have implications when we consider the most extreme case of neutron-rich systems, as in neutron stars. So short-range correlations can affect the properties of dense neutron-rich matter, and in particular, the symmetry energy, which is related to the difference between the energy per nucleon in pure neutron matter to symmetric nuclear matter. Now, again, due to their close proximity, SRCs are expected to be important at densities which are larger than the saturation density, up to several times the saturation density, where clearly we can see here the symmetry energy is not well constrained. So some initial calculations have been performed in the recent years to see how SRC affect the symmetry energy. Here we see an example based on a phenomenological non-relativistic approach. So the single nucleon momentum distribution for protons or neutrons is separated into two parts: the low momentum mean field part up to their corresponding Fermi momentum, and then a high momentum tail above it. The fraction of high momentum nucleons was taken either from experimental data, about 25%, or from microscopic calculations, about 12%. And this can then be compared with the commonly used free Fermi gas model, which is basically just a step function. Based on those momentum distributions, the symmetry energy was obtained as a function of the density up to several times the saturation density. So first, the result based on the free Fermi gas model is shown here by the black line. And in red and blue, the results based on the distributions that include the high momentum tail. Now, also for comparison, predictions from constraints from heavy ion collisions around the saturation density are shown, where at this region, in principle, all free predictions pass through them, but they behave very differently at high densities, where indeed SRC effects are expected to be significant. So in both cases, with different fractions of high momentum nucleons, the symmetry energy is reduced compared to the free Fermi gas, so gets softened, where the reduction is more significant for a larger fraction of high momentum nucleons as determined from experimental data. And this leads me to our new strategy in order to study short-range correlations in more neutron-rich nuclei. So instead of using direct kinematics, where we shoot an electron beam on a target nucleus, move to inverse kinematics. So shooting a nucleus on a target proton. By doing so, first of all, the use of hadronic probe increases significantly the involved cross-sections. Then, more importantly, in inverse kinematics, we are not limited to stable nuclei and can use radioactive-ion beams, which means larger N over Z asymmetry, and also study the isospin asymmetry dependence more systematically by considering isotopic chains. Now, a great advantage of inverse kinematics is that it allows to perform a kinematically complete measurement. So detecting in the final state not only the nucleons, but now also the residual A-2 system, which is not feasible in direct kinematics due to its low kinetic energy. So the technique of quasi-free scattering in inverse kinematics has been well established in the recent years in order to study the single nucleon structure of exotic nuclei. In the example here, we see actually the benchmark measurement, which was performed with the symmetric carbon-12 at energy of about 400 MeV per nucleon at the R3b setup at GSI. In such a case, after a proton knockout from carbon-12, this leads to two outgoing protons in the final state, together with the residual A-1 system, a boron fragment, where all three are measured in coincidence. Then, for example, by measuring the momentum distribution of the boron-11 fragment, one can get access to the intrinsic momentum of the knocked out proton inside the carbon-12 nucleus. And later, this was extended also to radioactive nuclei. So in 2018, we performed the first pioneering experiment in inverse kinematics at the BM@N setup at Dubna, using again the well-known system of the Symmetry carbon-12, but at higher energy of about 3 GeV per nucleon. And in this experiment, in principle, we had two main goals. The first was to show the feasibility to access single nucleon properties in inverse kinematics at higher energy compared to previous measurements. And the second and main goal was to identify SRC signal for the first time in inverse kinematics. So here we can see schematically the experimental setup that was used. The carbon-12 beam enters the setup, and after a reaction with a proton target, the two outgoing protons were measured in a two-arm spectrometer in coincidence with the residual fragment. Now, in this measurement, actually, in the case of an SRC pair, the correlated partner was not measured in a coincidence. So we start with the single proton knockout, and by writing the energy and momentum conservation between the initial state and the final state, similar to electron scattering, we define the missing momentum of the reaction, which without initial or final state interactions represents the initial momentum of the knocked out proton in carbon-12. And we start from the inclusive channel, meaning the coincidence measurement of the two outgoing protons only. So here we can see the opening angle between the two outgoing protons versus the missing energy. We have a large contribution from inelastic scattering. Then the second ellipse here represents the expected quasi-elastic peak region, which is not well visible. And this is due to the large contamination by the initial and final state interaction. So basically from two-step reactions. Therefore, we continue to the exclusive channel by requiring a coincidence of the residual A-1 system, the boron-11 fragment. Now the distribution becomes extremely clean, where clearly the initial and final state interactions are completely suppressed, and both the inelastic and quasi-elastic peaks are well visible and separated. And this then allowed us to select the quasi-elastic events, which showed good consistency with both the theory and previous measurement. So in the next step, we look at SRC events. Now, although the correlated partner was not measured in a coincidence, we selected a specific kinematics in order to ensure that the events are coming from SRC pairs and identify the SRC channel by a coincidence, in this case with the residual A-2 system. For NP pairs, this corresponds to boron-10, and for PP pairs to beryllium-10. Now, overall, we measured 23 events with boron-10 and only 2 events with beryllium-10. And although this statistics is very low, this is still consistent with the NP dominance that we saw before. Now, for boron-10 events, NP pairs, we can also look at some characteristics of SRC pairs. For example, the reconstructed opening angle between the two nucleons, which shows a clear back-to-back correlation, while at the same time, the opening angle between the boron-10 and the reconstructed relative momentum between the nucleons do not show any correlation and is rather flat, as expected from the scale separation. So the factorization of the SRC wave function and the A-2 system. So overall, this experiment demonstrated the proof of principle to study SRC in inverse kinematics and opened the way to go to radioactive nuclei. So about 1 year ago, we performed a pioneering experiment with a radioactive ion beam at the R3b setup at GSI using the exotic carbon-16 nucleus, as well as carbon-12 as a reference. Now, thanks to the large acceptance and versatile usage of the R3b setup, it will allow to perform the first fully exclusive measurement, including the 2 outgoing protons, the residual A-2 system, but now also in a coincidence, the correlated partner. So either a recall proton, which was actually made possible thanks to a group from LEAP, as I will show in the next slides, or a recall neutron. So the carbon-16 beam enters the setup from the fragment separator at GSI and is identified and selected. Then we have the target area, which was composed from a liquid hydrogen target, which was surrounded by 2 detection systems for the outgoing protons. Silicon strip detectors for tracking of the protons, and the Khalifa calorimeter for energy reconstruction. For the A-2 system, first it is tracked before the glad magnet, then it is deflected in the magnetic field and tracked again at the focal plane using fiber detectors. And this basically allows to reconstruct the trajectories of the different fragments and therefore their momentum over charge ratio. Then combining that with the charge information measured by a time of flight wall, we can see here a preliminary identification of the different fragments. Finally, again, the idea is to perform a complete kinematics measurement, including the recall nucleon. So for the case of a recall neutron, it continues through the glad magnet and measured in the large acceptance Neuland array, which currently includes 13 double planes of scintillator layers and provides a very high detection efficiency. Then for the case of a recall proton, it is deflected in the glad magnet and measured in a resistive plate chamber, RPC. And in fact, this detector was completely new in the R3b setup, and it was transported to GSI and operated by a team from LEAP, which is led by Alberto, Daniel, and Manuel, where Manuel is also currently analyzing data from this experiment. So the main goal of the experiment is to identify and characterize SRC breakup events from carbon-16 via the 2 main reactions of interest, NP pairs that will be accompanied by a boron-14 fragment and PP pairs by beryllium-14. Now, in addition, using the reference measurement with carbon-12, we will be able to extract the correlation probability, the high momentum fraction that we saw before from electron scattering, but with 2 advantages. So first, a larger neutron excess, and second of all, a much smaller mass difference compared to electron scattering, where we had to compare a heavy nucleus such as lead-208 to a light one such as carbon-12. And overall, a successful outcome from this measurement will allow us to extend it to the full isotopic chain of carbon, and then also to heavier nuclei. And with that, I will finish, and I would like to thank you for your attention, and I'm happy to answer and discuss any question or remark that you have.